So now we would like to cover the final topic of our this week's lecture, which is the MOS capacitance. So basically, a MOSFET, the NMOS or the PMOS device, have many capacitances that are inherent to the device. So first, basically, we know from basic electricity that electricity theory that any two conductors separated by an insulator have capacitance. So um, if we have two conductors and these two are conductors and they are separated by any kind of insulator material, so it could be air or it could be anything that does not conduct electricity, then we say that there is a capacitance here. So in an NMOS device or a PMOS device, in a general MOSFET device, there exists many kind of capacitances. So the first one is the gate to channel capacitor, and which is called the gate capacitance, and which is very important to us because it creates the channel charge necessary for operation. So if you recall from the previous lectures, the structure of a MOSFET, which in cross section it looks like this. So this is our insulator material, and on top of it we have our gate. So this is our gate, this is our source and drain, and this is insulator or silicon dioxide, and this is our body. And this gate capacitance is required to create a channel underneath the gate. So here is the channel. So this channel is formed when we because of the gate capacitance, when we apply some voltage at the gate, some because of the capacitance, the charges are uh, stored underneath the gate, so that helps us create the channel for the current to flow in the device. But another kind of capacitance is also present in the MOS devices, which is the source to body and the drain to body capacitances, and we call them the diffusion capacitance. So as from the color suggests, this diffusion capacitance is bad, but the gate capacitance is good. So this diffusion capacitance is created across the reverse bias diode. So in any if you look at the construction of an NMOS device, these two terminals are N plus and N plus, but the body is P type. So we have a reverse bias junction between source to body and between drain to body as well. So across these reverse bias diodes, there exists a diffusion capacitance, and this is called the diffusion capacitance because it is associated with the drain and source diffusion layer. And also remember that the NMOS body is connected to ground and the PMOS body is connected to the supply. So sometimes the diffusion capacitances could be for the NMOS device, as the body is connected to the ground, our diffusion capacitance sometimes appear across the source and the ground. And the PMOS device body is connected to supply. That is why sometimes the diffusion capacitance of the PMOS device appear across the VDD. So let's just look at the NMOS example here for short. If we have the NMOS transistor like this, and this is the gate, and this is the source, and this is the drain, and so each of the source and drain terminals should have a capacitance across the ground. So this is one, and this is another one. So similarly for the PMOS devices, these two capacitance would be connected across to the VDD. So first, the gate capacitance. So gate capacitance is denoted by Cg, and Cg is G. Basically, Cg is epsilon oxide times W times L times over the thickness of the oxide. So this epsilon oxide and T oxide is denoted as um, capacitance oxide times W times L. And sometimes we combine these two terms to rewrite this as C per micron times W. So this C per micron is just it just says that um, how much our capacitance, our gate capacitance increases um, as we increase the width of our device. So this picture shows us the again what the dimensions are of an NMOS device. So we can see that the width of the NMOS device is calculated like this, and the length of the device is just calculated like this. So the CG is proportional to the width of the transistor, and whenever we have wider transistors, our capacitance will be greater. And a typical value of C per micron is 2 femtofarads over millimeter. And finally, we have the diffusion capacitance. So the diffusion capacitances are source to body, which is CSB, and the drain to body, which is CDB capacitances. So these are the undesirable, and these are sometimes called the parasitic capacitance. So this capacitance is based on the area and the perimeter of the diffusion layers. So here we have an example of two NMOS transistors, or any NMOS or PMOS, two transistors in general, two MOSFETs in series. So in the first case, when we have we know from earlier lectures that whenever a diffusion layer is crossed by a polysilicon layer, then we have a transistor. So this is a transistor MOSFET. So we have two MOSFETs like this in series here, but in this case we have isolated diffusions. So and we connect the two transistors using a external metal layer like this. So this scenario is called two series transistors, but in isolated diffusion regions. So we can see that the area of the diffusion layer is very high in this case, because we need this much area for the diffusion layer. And in the second case, we have a shared diffusion layer, but we also have a contact in between. So because there exists a contact in between, we need to maintain some aspect ratio or maintain some area. So that is why we have cut down the area of the shared diffusion layer, but nonetheless it is or exists there. So this is also two MOSFETs in series, but now we have a shared diffusion, but with a contact in between. And in the third case, we have two NMOS transistors in series, or two MOSFETs in series, but we have a merged diffusion here, and which means that no contact is here in between the two transistors. So so in this case, the diffusion area is much smaller than the either of the two cases. So in the first two cases, if the width of the diffusion is W in every case, in the first case the the area of the diffusion layer between the two transistor is 5 plus 5, which is 10 lambda times W. And the second case, we have because of the shared diffusion, we have 6 lambda times W, And in the third case, we have 3 lambda times W. So you can see that as we go from left to right, we are decreasing the area of the diffusion layer that exists between the two transistors, and thus we can lower the parasitic capacitance that exists in the diffusion that the diffusion capacitances. So just to recap, so we use smaller diffusion nodes, so which is explained by the example here on the right. And in the case of the contacted diffusion, the C, in this case, whenever we have the contacted diffusion here, the CSB and C dB, source to drain and source to body and drain to body capacitances, could be approximated or comparable to the CG value that we calculated earlier. And in the third case, this is for the second case, and for the third case, the CSB and CDB value is comparable to half of the value of the CG that we calculated earlier, because it has much lower area than the previous two cases. So that is all for the MOSFET capacitances, and we'd now like to show some of the numerical examples for the MOSFET transistors. So thank you.